Hi, I'm Professor Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah. And today I wanted to go over an example where you have multiple components, inductors, capacitors, along with AC sources in the circuit, and how you go about solving this type of a circuit. So in this example, we want to find the actual voltage, either V1, V2, or V3, and we're going to solve for V2. And so the first step you're going to do is transform all of the input signals and the capacitors and inductors into the frequency domain. Here you already see that they've been converted for you, which is shown by the J's. So minus 3J is already been transformed into the frequency domain. So we also need to transform the signals. So we need to transform the VS and the IS. So our VS is going to be 3 milli EJ 20 degrees, and IS is going to be the 7 milli E to the minus J 15 degrees. So these are our signals in the frequency domain. So to analyze this, we're going to use node voltage. We need to write a node voltage equation at V1, and then one at V2, and then one at V3. So at V1, we have the current here, which will be V1 over 6K. We have the current here, which will be V1 minus V2 over 2J plus 2K. And we have this branch, which will be V1 minus V2 over 10J minus 3J. And that is all the branches that we have for V1. So our next node is at V2. We're going to have this current here, which will be V2 minus V1, over the summation of those, which will be 2K plus 2J. We have this one, which will be V2 minus VS, and remember that we need to note that VS is written in that phasor form. So that's polar form, 3 milli EJ 20 degrees, divided by 4K. We have this branch, which will be V2 minus V3 over minus 5J. And this branch, which is a minus IS, and again, we need to write that in the polar form. And we also have this branch here. So that's going to be V2 minus V1 over the summation of those, which is 10J minus 3J for 7J. And that completes all of the branches off of V2. For V3, we're going to have this branch, which will be V3 over the summation of all of those, which is 3K minus 5J. We have this branch, which is V3 minus V2 over minus 5J. And then we have a plus IS, and again written in polar form. So this gives me the three equations. And so this gives me my three equations, and now I want to write them in matrix form. So the matrix form looks like this, where we're going to do have the order of V1, V2, V3. So with that, we can go back to, so looking at the first equation, so looking at this first equation, we're going to use all of the ones that have a V1 coefficient. So that's going to be 1 over 6k, 1 over 2j plus 2k, and then plus 1 over 7j. V2 coefficients are going to be the V2 and this one. So we're going to have a minus 1 over 2j plus 2k and a plus 1 over 7j. And we don't have any V3s in this equation, and we don't have any constants, so that one's 0. So for this one, we have V1 here, and we have V1 here. So we have a minus 1 over 2k plus 2j, and then a minus 1 over 7j. And for V2, we have this term, this term, this term, and this term. So we have 1 over 2k plus 2j, 1 over 4k, a 1 over minus 5j, and a 1 over 7j. For V3, we have this term, and so we have a minus with a minus over it is a 1 over 5j. And then we need to take the constants over to the other side. So we have 3 milli, which is 3 times 10 to the minus 3, e to the j 20 degrees, and then a 7 milli, e to the minus j 15 degrees. And that is our second equation. The third equation, we don't have any V1 terms. V2 we have here. So a minus over a minus again becomes a plus, so 1 over 5j. And then for V3, we have 1 over 3k minus 5j, and then a 1 over minus 5j. And then we have the constant, which we need to take over to the other side. And we set up our matrix to look like this. So once we get the matrix form, we're going to call this our A, and this is our B. And then we use MATLAB to solve that. I'm going to show you if these were the values. These are not the correct values, but if these were, you would set up your A matrix, you would set up the B matrix, and then you would use inverse A matrix times B, and you're going to get an answer. These are going to be in the same order that you had for your matrix. So that order in the answer is V1, V2, V3. So this is the answer for V1, V2, and V3. I can use this function in MATLAB, cart to pol, to convert it from the Cartesian plane to the polar form, which is what we need if we are going to write the answers for V1 of t, V2 of t, or V3 of t. So remember that theta is in radians, and if I want to do it in degrees, I need to change from radians to degrees by 180 divided by pi. And so if I want to write, say I want to write V2 of t, I'm going to use the R value for my amplitude, so that's going to be 0.89. It's going to be cosine, and I'm going to use the omega from the original. So going back up, the omega was 200. So we saw that omega is 200, so 200t. And then we can change that from the 2.5 radians by multiplying it by 180 degrees over pi. And that gives 143 degrees. So we can write this as 143 degrees, and that's all in volts. So that would be our V2 of t. And you could write this also for V1 of t and V3 of t. I just wanted to show you the example. So this concludes this example. Thank you for watching.